Hello, everyone. Let's now continue our discussion about the next topic, the Heisenberg Uncertainty Principle. So, the uncertainty principle is commonly expressed like this: delta x multiplied by delta p is greater than or equal to the Planck's constant over 4 pi. So, what this means is that the uncertainty, if we know, okay, x is the uncertainty in the position, and p is the uncertainty in the momentum for a particle, and more importantly, for an electron. Okay? So, what does this mean? Well, it means we cannot measure the position and momentum with great precision simultaneously. So it's like this, right? When we say the electron can occupy two states, right? We can know it's like we can say yes, okay, it's going to be here or here, but we can't specify with any certainty that when it will be here or when it will be there. It's impossible to know because the particle is so small, and we cannot determine the position, both the position and something's speed. For example, we think we can do that given if we know how fast an electron is moving versus and its position, but in reality, we don't know how fast an electron moves, right? It's a very small particle, and it's very hard to detect. And it's not like you can measure its velocity, normally speaking, right? Because it's not something we can see. Okay. And so, what this uncertainty principle states is that that in experiment we can only determine the precise location or the momentum, and we cannot determine both. Okay, so this is a very confusing concept, but it's one of the basis of quantum mechanics because quantum mechanics, we know the electron is somewhere, but we can't know everything about the system. So that would make quantum mechanics very puzzling because in classical mechanics, if you know everything about the system, you can predict where it'll be or what the speed will be. For example, a car traveling at a certain speed, right? So, in more simple terms, if we know precisely where a particle is, we cannot also know precisely where it has come from or where it's going. Because in quantum mechanics, remember, particles can be in two places at once, just like we saw in the video. So it's very hard to kind of understand particles or electrons, pretty much, like how they behave. It's very hard to predict. Okay, so if we know precisely how a particle is moving, we know it's this speed, right? But we cannot know with great precision where it currently is because it's so small. It's going to be moving at such high speeds. Okay, so let's kind of make this analogy. In the subatomic world, electrons behave like waves, right? Just like we saw with the diffraction experiment or the double slit experiment. So waves move all over the place, just like waves in the ocean. We do not know where exactly the particle is, so the more wave nature an electron has, we don't know exactly where the particle is in the wave, right? We just know it's somewhere, and as you see here in this example, the waves can combine into a wave packet here, and then so say an electron moves a certain way, right? But once it moves like through different mediums, it'll have a different like waveform, and so when those waveforms kind of combine over time, the electron, we can't really predict where it will be. We can kind of predict, like, probability speaking, we can predict where it may be, but the waves won't tell us pretty much the exact location. We can only get a general idea where it may be, right? And that's because of the wave-like nature of the electron. It's not a particle, so that's why we can't know with great precision both its speed and location. Okay. So yeah, I think this kind of description here kind of sums it up perfectly, and I'll kind of break it down for everyone. Okay. So so say we have a lot of wavelengths, right? Um, the more wavelengths we have, the more likely is we know where the particle is. But you see all these wavelengths, depending on how the electron moves, right? The wavelengths won't all be equal. So essentially speaking, like if we have a lot of information about where the electron may be based on like where the wave the picture or the image of the wave, we can kind of we could kind of superimpose them and make it more localized where the electron may be. But if the waves are all different, they'll have different speeds or momentum, and that'll make it harder for it to predict like how fast the electron's going, right? So, for example, say we can use a number of waves to describe the location of the electron. Okay, that'll give us an average wavelength, but it'll tell us, okay, the electron is probably somewhere here. But when we do that, there's nothing to be said. There's little to be said about speed because all these wavelengths, as we see in this picture, they're all different. They all have different speeds or different momentums, right? That means it's more uncertain, like how fast we don't really know how fast the electron's moving. So I guess to put it more simply, if you think about really small particles, right, they can do things that not really small, particles. They have more wave-like characteristics. So while they are particles, they behave more like waves. So the more we know about something, the location, for example, for an electron, the less we know about speed, because when waves interact with each other, they can influence their speed, and when they interact with matter, it can influence their speed. So if anything, when we see a wave, kind of float across the water, we can kind of guess, like, okay, the water is moving at this speed, right? But we won't be able to determine like where the water, like say I'm talking about like a single particle in the wave, right? We don't know where it will be in this time point versus this other time point, because while we know it's moving this fast, the electron could be anywhere in any part of the wave, so it's harder to tell where it may be. And I think that's kind of the best way I can kind of explain it. It's not a very satisfactory answer. Even Einstein had a problem with this. He spent most of his time, latter part of I think of his life, until his death, pretty much trying to disprove it, because he didn't really he couldn't accept that there wasn't a theory to tie in both the location and speed or momentum of a particle. So he kind of couldn't accept that. So what I think the important part is that we must keep an open mind, and that the theories for such difficult concepts will come to us, or will reveal themselves to us when we have when we get the data and observations to kind of form a theory around it. It's like saying, don't try to make the data fit the theory. Let the data formulate the theory. And so, but quantum mechanics, I think, is one of the more trickier subjects, I would say. Okay, so that's the uncertainty principle. So just think of it like you have a very tiny particle, right? You have a tiny. If you can't see the particle, right, it's hard to predict. So if you can't see a particle, right, but you know its speed, it's going to be very hard to predict where it'll end up, right? Because you don't know its original location. It could be anywhere in the region of space where you think it is. And then if you say, okay, so the particle's in this location, in this orbital, in this energy level, we know it's there, okay? But we can't predict how fast it's going, right? Because we only know its location, right? We don't know anything about its speed. Just because we know its location doesn't mean we know anything about its speed, right? Because if we compare it to a larger particle, say something that physically exists in reality, like say a car, right? We know the car has this certain speed, right? We can record its speed. We see it. We know how fast it's going to go. Okay? And then at a certain point in time, we say, okay, it's traveling this fast, and it'll be at this point, if it keeps going straight on the road, it'll be at this point at time t, right? But for the electron, we can't really say that, right? Because we know, when we think about electrons, we can say something about speed and say, okay, it's moving this fast, so but we can't say anything about its location. So if we know its speed, we know its location, but very little, right? So it just has to do with things that we can perceive or not. So if a particle, if we know much about the particle speed, we cannot determine its distance. Okay, so the uncertainty in the distance increases for quantum mechanics because these particles, they don't behave as true particles. They behave more like waves. So and with like waves, we can only know pretty much its speed, right? Mostly its speed. Never pretty much. We can't predict the location of a wave based on just its speed alone, because waves, they're not physical. They're not really particles, so they don't really they don't just stop when they hit other objects. They actually change their kind of their movement. So it's kind of hard to determine both the speed and the location of, say, something that's very wave-like. Okay, so I know that was confusing. We'll talk more about this in discussion. So if there's any questions, please let me know. It's a very confusing topic. I would agree. Okay. All right, now let's move on here. Okay. So let's put this equation into practice here. Let's calculate what is the wavelength associated with electrons traveling at 1/10 the speed of light. The mass of an electron expressed in kilograms is this value here. Okay, and we know that 1 joule is equal to a kilogram per meter squared, second meter squared per second squared. Okay. So, okay. So this is now, so remember when we talked about de Broglie wavelength? We know that wavelengths, they have, we can calculate the wavelengths based on the mass and speed of a particle. So electrons will have the form lambda equals h over mv. So mv this time is velocity. Okay. So we can solve for velocity here. So the velocity is it's traveling at 1/10 the speed of light. So 1/10 will be 1/10 times the speed of light, 2.998 times 10 to the 8th meters per second. Okay. So this gives us about 2.998 times 10 to the 7th meters per second. Okay? All right. So now we know we have to first convert H into kilograms. So we need to convert from joules to kilograms. So we know that H is equal to 6.626 times 10 to the negative 34 joules. But joule seconds, right? But we can convert this to 6.626 times 10 to the negative 34 kilograms times meter squared time per second squared. And then multiply that by the seconds, okay? And this would equal 6.626 negative 34 kilograms per meter squared per second. Okay. Now, if we put everything together, we will get lambda equals 6.626 negative 34 kilograms times meter squared per second squared. Oh, sorry, per second, sorry. And then divide by the mass times velocity, we get 9.109 times 10 to the negative 31 kilograms. And then the velocity will be 2.998 times 10 to the negative 7 meters per second. Sorry, I'm losing it today. So the kilograms will cancel here. We turn our meters now into meters here, and then the seconds will cancel. Okay? And so then our wavelength here is 2.42 times 10 to the negative 11th meters. Okay. Now, if we imagine this was an object that was much larger and traveling much slower, we can actually get some useful information out of that. E negative 34 divided by, let's say, a 50 kilogram object. And then it's traveling at, let's say, 200 or, maybe 10,000 meters per second. Okay, so yeah. So, when we're talking about heavier objects, they tend to have wavelengths that are infinitesimally small. So when we have wavelengths that are really, 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 really small, that kind of tells us that they don't exist primarily as waves. They probably have more particle-like in nature. So if we were to think about this equation, right? If you had a heavier object moving at a slower speed, you'll actually get wavelengths that are so small that they that you would think they would move faster um, if we were considering them waves. But the truth is that usually when objects have really small wavelengths, using this equation, de Broglie's equation, we kind of just assume that they'll behave more like particles because their masses are so massive that if they were to have a wavelength traveling at a certain speed, it will be so small that that will be almost impossible to detect them as waves. Okay, so this is a good exercise to kind of think about. Like, okay, so if these molecules behave at like waves, they should have wavelengths within the region of nanometers, or that can be that can have energy associated with light. So usually in this case, we see that for stuff like electrons. Okay. So I would say the heavier the object or particle, the more like it represents a particle because it has energy. And then the lighter the particle is, like the smaller the particle is, the more likely it will behave like a wave. And that's why we see electrons behaving like waves, because of their duality from light. Okay. Okay. So let's end things there, and we'll pick up on this part. We'll pick up next week on we'll do an example on the uncertainty principle, the Heisenberg Uncertainty Principle. So let's stop here for today. All right, I'll see everyone next time.